Okay, the next topic is we are going to talk about the solutions of the homogeneous equation for linear system. If we have the general equation as this function, as I said, for the linear system, you have dependent variable more than one parameters. For example, in this case, we have y1, y2 to yn. So that's why we have n equation of the homogeneous differential equation. And we have only one independent variable, which is t. So the way to solve for this linear system, this part of the linear system, we are going to write the linear system in the terms of matrix. So here we will get a matrix like this. And the way to find the solution, we can do it by assume y1 is equal to k1 times exponential of the lambda t, whereas lambda is a constant and k1, k2 to kn is a constant too. So now our solution would come as a bunch of the solution because we have n terms of y. So we would have n solutions. From our assumption, we are going to plug the value of y1, y2 to yn back into our linear system. So if you take a look at our linear system, it is the first order differential equation. So each term of y solution, y1 to yn, we are going to do the first derivative of those terms. So for y1, the first derivative of y1 by dt would be equal to k1 times lambda times exponential of lambda t, right? And then we do it with y2, y3, and yn. So for y2, we would get k2 times lambda times exponential of lambda t. So likewise for y3, y4, until yn. So for yn, we would get kn times lambda times exponential of lambda t. So what do we do next? It's just that we plug the terms of the first derivative of y into our solution. So we will get here k1 times lambda times exponential of lambda t equal to, and you just repeated the terms on the right hand side of your differential equation, and you got to plug the value of your y1, y2, until yn in there. The terms of matrix of A, which is a11, a12 until a1n, a21, a22 until a2n, and so on, and the last one is the an1, a2 until ann. This is the matrix of the coefficients of y. You would see that for the first equation, the term of k1, you have two terms of k1. You just move the term of k1 to the same side. Okay, and then set the right hand side equal to 0. Okay. So second equation, you would have the terms of k2. You move the k2 into the other side, put them together, and then if you rewrite it again, you would get the set of the equation like this. This one, after you see, you move k1 here to this k1, you have exponential of lambda t for both sides and k1 for both for both terms, and then the inside you would have a11 minus lambda, right? And then this term times with k1 times exponential of lambda t. But the rest of the term would be the same, which is equal to 0. And for the second equation, you take this term and then put it with this term, so you have k2 and exponential of lambda t, the same for both terms, so you take it out. So you would get, the first term is still the same, and the second term you would get a2 minus lambda, and the whole thing times k2 times exponential of lambda t, and the rest of the term still be the same, right? Because you don't have any extra term of other k. And then set it equal to 0. Do it. So if you see from here, the terms on the trigonal would be the terms of the coefficient of a11 minus lambda, a22 minus lambda. This one would be a33 minus lambda, a44 minus lambda, and the last term is an minus lambda. Remember that divide every equation with exponential of lambda t. You see every term here has exponential of lambda t. And every equation has the same term, which is exponential of lambda t. So it said that in that case, I'll divide every equation in here by exponential of lambda t. So I would get another set like this. And it said that from whatever we see in here, the determinant of a minus lambda I times k equals to 0. From this, a can be 0. K can be 0, right? Because k is a constant here. If k1, k2 until kn is equal to 0, then your answer would be equal to 0. It's called trivial solution. So from this, our k can be 0. So in order to make this sentence true, only term that can be 0 is the determinant of a minus lambda I. And this will be our characteristic equation. From this, we can find lambda, because a we know, I is the identity matrix, right? I is identity matrix. So from this, only lambda that we don't know. And lambda would be a number. So in this case, they're saying that they are going to divide the case into 3 different cases. The first case, if lambda is unrepeated real numbers. If your lambda is unrepeated real numbers, so you would find the lambda from this equation as a lambda 1, lambda 2, and 2 lambda n. You would get n lambda, because now you have the n terms of y. So you would get n values of lambda. How do you get n value of lambda? From this characteristic equation. So the idea itself is pretty much the same as the previous chapter that we have learned. But the difference is that with the linear system, you have n values of y. You have n terms of y, so you would get n values of lambda. So in that case, when you find n values of lambda, so your y1 is equal to k1i times exponential of lambda 1t. For y2 you got lambda 2, and y3 you got lambda 3, and yn you got lambda n. And then the way to write down the solution of your linear system, you write down as a matrix. Y1 until yn is equal to C1, K11, K21 to Kn1 times exponential of lambda 1t plus C2 times K12, K22, K32, K42 until Kn2 times exponential of lambda 2t, and plus until the last term is Cs times the constant times exponential of lambda n t. That is the case 1, which is the simplest one. Okay. Let's take a look at the example.